All right. Well, it's a great pleasure to be here. Thank you so much for joining. I want to talk about something that's evolving quite strongly in Java and want to share some thoughts about it. If you look back in time, it's kind of shocking to really think about that Java has been around for 30 years almost. I don't think any language, well, let me put it this way. I don't think any good language survived this long in terms of the history of programming. Sure, you could say COBOL has been around for a long time, C++ has been around a long time, but which good language has been popular for this long? However, one of the things that is absolutely phenomenal about Java is that it's evolving and trying to provide us what's right for the current times. It's incredibly hard to design something that lasts for several decades, so the languages have to evolve to support it. And one such evolution is in the area of concurrent programming. We all talk about parallel versus concurrent all the time, and I think in general, we could agree that it's very confusing when we talk about parallel and talk about concurrent, isn't it? So what's the difference? I just demonstrated it, if you noticed it. I just demonstrated parallel versus concurrent. And that is, thankfully, I can walk and talk at the same time. I don't have to stop walking to say a few words. I don't have to be quiet as I take steps. I can talk and walk in parallel. However, I dare not, and I wouldn't do this, try to drink water and speak at the same time. That can be dangerous to health, but definitely not civil to talk and drink. There's some people who are capable of doing it, but we won't talk about them here. There are things you can do in parallel, but there are things you can only do concurrently. But if you look at a duration of time, both parallel and concurrent make progress during the time. I'm not going to speak for 30 minutes and then quietly drink water for 10 minutes while you watch. That'd be really, really boring. However, as I'm saying a few words, I may get thirsty, I may take a sip, 1 or 2 sips, I may say a few words, then take a few sips. That's why it's concurrent. Both the tasks are progressing in the given amount of time. But of course, we've been doing concurrent and parallel in Java for a very long time, in fact, from day number 1. However, in more recent times, we are shifting our focus to something completely different. And the reason why we are doing that is that the architectural shift that's happened over the past several years. Today, we are more focused on building distributed architectures, whether it's a monolith distributed across machines, or a microservice that's distributed across machines, or various other architectures that we often talk about. So what that means is you are performing calls to a web service or a microservice or to a remote system to get back some data and continue. And as a result, more than parallel and concurrent, we really need to think about asynchronous programming. Now, I don't want to say this twice because it's really hard to say it, so I'll say it only once, but if you ever quote me, I will tell people I never said this. JavaScript got it right. I'm not going to say this again. Now, I know it breaks our heart to know that something as evil as that can get something right. But they did get it right. And what a bold step to say, we're not going to focus on parallel and concurrent, but we're going to provide asynchronous programming. Well, when I said they got it right, they got the idea right. The implementation was a disaster. That's a different story altogether. And the point really is that we want to really be able to do asynchronous. But what is really asynchronous programming? Well, we'll come to that in just a minute. But don't we have threads already? Well, sure. But remember, threads are lightweight. Way back in time, before some of us in this room were born, we used to create processes after processes, things like CGI. That was horrible, very slow, not very efficient. Well, multi-threading gave us that ability to spin threads very quickly and use pools of threads. So threads are considered to be lightweight. But the word lightweight is very relative. It's like a little kid. You could say, oh my gosh, the kid is heavy today. Well, that doesn't mean the kid is heavy like a adult, but they are heavier than they were before. So the word lightweight is really relative. But we all talk about doing multi-threaded programming, but why are we talking about it? Now, let's step back for a minute. Everyone in this room has written sequential code, right? Well, actually, I'll remind you how it feels to write sequential code. If you're writing sequential code, you actually smile at other people at work. That's how you know you're writing sequential code. People are generally happy. You go to lunch together. You write code, and it works. That's usually what sequential code is. And you've been writing the sequential code for a while, and then you realize it's a bit sluggish. You click on a button, it doesn't respond anymore. You make a request to a service, it's very slow, dragging its feet. And somebody at work says, we got to make this better. We got to make this responsive. We got to make this multi-threaded. That moment is when the last time there was joy at work. Because all of a sudden, the code turns into a monster. And you're looking at this code and you're telling yourselves, this code used to be easy to understand. This code used to be where I can actually see the entire code. Now there's lock and synchronize everywhere, and you have no clue what the code is doing. And you are struggling with this code. It becomes harder to understand, harder to maintain, and even worse to debug. And late in the night, while you're debugging that code, you decide to apply for this other job. That's called concurrency, isn't it? So you're like, no, this is a horrible way of writing code, but we all have gone through it, but why? The reason why we did that was, unfortunately, threads were really inefficient. So what did threads really do? When a task of execution takes some time to execute, the thread of execution blocks along with the task of execution. That is the problem we are dealing with. So when the thread blocks, when the task blocks, what do? Oh my gosh, the thread is blocked. It's not doing any work. So we need to create more threads. Think about this for a minute. The threads we created suck, so we'll create more of that. That sounds like a government program, right? Not like a good software idea. But that's exactly what we've been doing, is we've been spinning threads because the ones we spun already are stuck, so we keep creating more of them. Well, unfortunately, what's a consequence of that? Well, if the threads you created are blocked and waiting, the number of requests you can serve is limited. Because the number of requests is limited, and if you want to serve more requests, you say, let's go ahead and put this in a cluster of machines. This is fantastic news for the cloud providers. They're like, keep going. We'll tell you where to send your money every month. And your company keeps sending them money. Why? Not because you need the hardware to scale. It's because the threads suck. And as a result, you needed more hardware to scale. But in the meantime, we've been screwing the environment as well. What you can do in a machine, you have to do in multiple machines as well. Well, that's the state of where we have been in. But let's understand, what does it really mean to be asynchronous? So the question is, what is asynchronous, right? What does that even mean? So let's be honest about it. If you make a call to a function or a service that needs to respond, let's see, you have to block for the response to arrive. This is as simple as the fact, right? If I go to the coffee shop and I tell the barista, like to have a latte, please. And they say, sure, no problem. And they make the latte, they look like, where did Venkat go, right? I'm asynchronous. I'm going to order coffee and leave, right? That's not going to help anybody, right? So essentially, if I order coffee, I've got to wait for the coffee to arrive before I can drink the coffee. I can't drink coffee out of nothing. Just order coffee and you drink it. Doesn't make any sense. So a task that makes a request has to wait for the response to arrive. That's the nature of it. So what does it mean by non-blocking, right? So what does non-blocking really mean? Well, let's go with that same example for a minute. You took the time, you get to work in the morning, and at 8 o'clock you check into the office. Let's be honest, what's the very first thing you do when you put your stuff in your desk? Go get the cup of coffee, isn't it? So you go to that coffee machine and you are angry because the coffee pot is empty. Somebody who took the last cup walked away without refilling it. How dare? So I hope you don't do the following, right? You don't turn on the coffee machine, it starts brewing, and you just stand there and you stare at the coffee being brewed, and you don't move. Like the guys in the front of the Buckingham Palace, right? You're just stuck over there. And your colleagues come to you and say, hey, how you doing? You're not responding, right? And they're like, are you okay? You're not responding. And they're like, should we call the cops or the security? You're not responding. Why? Because you are blocking and waiting for the cup of coffee. I know some days you feel like doing so, but you wouldn't, right? So what do? You turn on the coffee machine, it's brewing coffee. You go to your colleague and say, hey, are you ready for the design meeting? And your colleague says, no, I need about 10 more minutes. All right. And you go turn on that email, it's downloading, and you're reviewing a document. And somebody says, hey, what are you doing? And you say, I'm waiting for the stupid coffee machine to have coffee in it. I'm waiting for my great colleague to be ready for the meeting. I'm waiting for the email to download, and I'm reviewing this document right now. That is the non-blocking you. So essentially, what does non-blocking mean? It essentially means when, right, the task blocks, and it always has to block. When the task blocks, the thread does not, you could even say, should not, right, block. So essentially, that is the idea. Let's think about this for a minute. What happens in Java when you say, for example, in Java, when you say thread.sleep 10,000, you're saying sleep for 10,000. What does the thread say? The thread says, what a great idea. Let's sleep together. And while your task is sleeping, your thread is sleeping with it. Anybody in this room who has ever had a toddler in their life, what is one thing you never do? When the toddler wants to sleep, you don't say, what a great idea. Let me sleep with the toddler. That's how your kitchen sink becomes a mountain, right? And all the things are waiting, and you never get any work done. So what do you do as an adult? Well, what do you do as a responsible adult? When the kid is sleeping is when you go do your work. And that's not what the thread does in Java. The thread says, when do you want to sleep, right? So this is very irresponsible, isn't it? And unfortunately, that doesn't quite cut it. So I want to just dig in and look at how this really non-blocking will feel like. This is very different from multi-threading. What we are saying here is not to keep creating threads, but to really make better use of the thread we create. So to understand this, I want to jump in and talk about a slightly different concept. We all know about subroutines. Subroutine is just a function you call, and you get a response back from the subroutine. But now we are talking about what's called a coroutine. A coroutine, as the name alludes to, is cooperating routine. So you have a routine that cooperates with another routine, and so two things can exchange and run at the same time. But to understand this, if you don't mind, I want to give you an example here in Kotlin, only because it's a little easier to see how this actually works. So let's go ahead and import Kotlin x.coroutines, let's say, .star, and I'm going to say run. And within this, I'm going to simply say, let's say print line, calling two tasks from, and let's go ahead and say thread. Let's go ahead and say thread.current thread, so we can see the thread that's being used to execute that particular call. Then I'm going to say called to task. So nothing really exciting yet in this code, as you can see. So we're calling to task, and we say we called to task. That's all we are doing. But then I'm going to call task 1, and if you will, I'm going to call task 2 as well. Oh, by the way, I forgot to mention this to you. Kotlin is a beautiful language. But not only is the language beautiful, I truly believe that the people who created Kotlin are some of the most amazing humans in the world. Because they don't want you to think about you writing code. They don't want to think about the code you write. They want to also think about you, the one who is writing code. I mean, how would it feel to go grumpy home after writing code? They want you to enjoy writing code. And to remind you that to enjoy writing code, they decided to turn their functions with a keyword called fun. Because every time you write code, you're having fun. Isn't that great? So you're writing code, how's it going? I'm having fun writing the code, right? So fun, task 1. And then you say here, let's say print line, let's say entering task 1, let's say from, and I'm going to say thread.currentThread, and I want to specify the thread I'm going to call this from, and I'm going to say exiting task 1 as well. Likewise, let's go ahead and say I want to call a task 2 as well. So when we run this code, nothing really exciting as you would expect. You're going to call the function, you called 1, you exited 1, you called 2, exited 2, you finish the whole thing. That is called sequential programming. That's also synchronous programming as we know it. But I'm going to modify this to run, in this case, blocking. And you may wonder, why call it run blocking? Because you just finished saying non-blocking. What the run blocking simply says, create a parent coroutine, a mom coroutine, and the mom coroutine says, I will be here until my children come home. So you can create child coroutines, but the mom coroutine blocks and waits for the completion of the child coroutines. That's what they call it as a structured concurrency in Kotlin. But it doesn't make any difference to our code at this point. I just changed the run to run blocking, but the output is exactly the same, no difference. However, I'm going to go back here and say launch, and I'm going to launch task 1 and launch task 2 as well. So what does launch do? I want you to think about the way back in time. I know this is hard for a lot of us. Way back in time when you did swing programming. Remember that? Or when you did Windows programming. What did you do? When you clicked on a button, you didn't run the code for the button handling right away. When you clicked on a button, you put an event in the event queue. And then when the current task is completed, it pulled the event from the event queue and executed it. Exactly the same concept. When you call launch, you're not launching anything. You're putting an entry into a queue saying, run this for me, will you? And the code runs till the end and says, am I done? Oh, no, you got an entry in the queue, go run that. So it's going to run that code, but only after finishing the current set of execution. So notice the sequence in the output this time. It says calling the task, but immediately said called the 2 task. Then it ran 1 and exited that, and ran 2 and exited it. So we already saw a difference, and we can see it is non-blocking. How is it non-blocking? Because the whole thing is in main thread, not anywhere else. However, to add a little bit more flavor to this, I'm going to go back and say delay 1,000, okay, delay 100, and I'm going to put a delay 100 here as well. So what does the delay say? I came in to run this, but I want to really pause for 100 milliseconds. When your task says pause, what should your thread do? Not pause. Because if a thread pauses, that's underutilization, isn't it? So at this point, the thread should immediately go over and do the dishes. Do other tasks. So that is the whole idea. But before I show this to you, I do have one complaint to make. I mentioned that I really, really like the people who wrote Kotlin. I do, but I wish they had thought about this a little bit further and not made this horrible mistake they made, in my opinion. They could have called me and said, Venkat, what do you think? I would have told them seriously what I think, because this function is a non-blocking function. If they had asked me, Venkat, what should we do with this? I would have said, non-blocking fun. That would be really nice, isn't it? Or I would have said, never-ending fun. Wouldn't that be nice? But it breaks my heart. They decided to call it suspend fun. This is serious stuff, right? When you're writing the code, and the minute you make it asynchronous, your face becomes grim. Like, are you okay? I was having fun, but I had to suspend my fun right now. Anyway, this is one of the things I'm hoping they will ever change and call it maybe never-ending fun, right? That would be really nice, or non-blocking fun. But anyway, you have to say suspend fun. Well, what does this do when you say suspend fun? In this case, notice the output. You are still entirely in the main. But you said calling the two tasks, call the two tasks, entering task 1, but you didn't exit task 1 yet, but you entered task 2. And then when you're in the middle of task 2, you hit the delay, and you go back and finish task 1, and then you're finishing task 2. So in other words, the main thread is multitasking, the non-blocking nature to switch between 3 or 4 different tasks and not waste its time waiting on one task to finish completely. So this idea of non-blocking is extremely powerful. And that is exactly what we want to do. So Kotlin is great. It gives us the structured concurrency, which is awesome. We can see how easy it was to implement the code. And there's a lot more to it than what I've shown you here. There is a hierarchy built into it. If one of the tasks were to fail, it propagates the exception to the parent, and the parent can then terminate the other children. So all of that is baked in. However, it also has a problem here. And that is, notice you had to annotate the function with the word suspend. What that means is you can only call asynchronous function from another asynchronous function. Now, what is the consequence of this? If you take a piece of code that is all synchronous and you decide to make it asynchronous, you have to keep changing these, all that to suspend. That can be annoying, to say the least, if not a lot of effort. Well, Java took a very different approach to provide this kind of idea. Let's take a look at what that actually means, so we can appreciate what that really provides. But before we do this, the question really is, you're in the middle of a function, and then abruptly you leave the function, and you go elsewhere and do some work, and you suddenly come back into that function, and you are continuing to run your code. And the beauty of this is, it may not even be the same thread that is continuing your job. Why not have one thread block and another thread continue? Let's take another example. Let's say you go to a restaurant and you are ready to have a meal. So you're with a group of your friends, you're sitting down in the restaurant, and the waiter comes over and says, what would you like to drink? And you say, what do you have that we could order for drink? And the waiter tells you a list of things, or says, flip over to page number 3. There's a lot of things we have listed. Those are the drinks available. And then you say, I'm really not sure what I want to drink. If this is not a good restaurant, what's going to happen? The waiter says, let me pull a chair, sit next to you. Let's talk about how your day is going. What are you in your mood for? And you're like, I don't know. On Tuesdays, I like to drink that. On Wednesdays, I usually drink this. But I'm not sure today what I want to drink. And the person is doing a counseling for you for the next 30 minutes. And in the meantime, everybody else in the restaurant is angry and they topple the tables and leave, right? That restaurant will not survive in business. Here is the irony. Good waiters don't actually wait, right? Good waiters make you wait while they go bus around multiple tables. So the threat in Java has been like a bad waiter. It comes to you and starts running and says, don't worry, I'll be here until you leave at the end of the day, right? And what about efficiency? That goes through the door. So the question is, how can one thread switch between another task and come back to this task and resume it? Let's take another silly analogy. Let's say you are in this hybrid work environment. You decide to go to work on Tuesday, but you don't have an office anymore. So what do? You find one open desk, you sit down and work on that for the day, and now you're ready to leave. Maybe you'll come after 3 days or the next week, but you got to a place to put your stuff. So what do? You probably take a box with your name on the box, you put your stuff in the box, and you put it in a corner and say, that's my stuff, nobody dare to touch it. And then you leave. And when you come back a few days later, you can take that box and put that stuff on your desk again, work for the day, and then pack it again and leave it. Well, that exactly is the idea of what threads will do. Threads will capture the state of a particular task, tuck it away, and then come back and pull it back in and run. And I call it box. They call it a continuation because that's more fancy. So continuation is a data structure that allows us to park our data only to restore it back for us to execute in the context of the same execution when it needs to resume and continue. So continuations are part of this idea from the ground up. Now, continuation is something you know about, but it'll be really, really a bad practice to give continuation to a programmer because everyone in this room knows it. The more power that's given to us, the more mess we create. So the wisdom is, know it is there, but don't touch it. So this is why continuation is a data structure that is there behind the scenes, but we're not going to touch it. Let me quickly show you an example of it. So I'm going to say compute, and the compute takes an integer, and it simply returns the integer. Nothing really exciting, as you can see. I'm going to say Kotlin C-JVM, and I'm going to compile the sample, and I'm going to say Java P, just to look at the bytecode, and I'm going to take a look at the sample class right now. And guess what? No surprise. What do you see? Compute is just a function that you have which takes an integer and returns an integer. Nothing really exciting, right? So that's exactly what Kotlin did. It wrote the function for us in the Java bytecode. Going back to this code, the only thing I do is to say suspend, right? So that's all I did. I annotated it with suspend. That's all I did. I go back and compile the code again. I look at the Java P one more time. And this time, what do you notice? The same function compute that you saw a minute ago, how does that look like? Well, look at compute now. It takes an integer, all right. But notice it also takes an additional parameter, which is continuation. So the compiler is working behind the scenes to provide the continuation so that when the task blocks, the thread can not have to block and wait, but stores the state elsewhere in a continuation. So when a thread comes and picks it up, it's got the data to move forward. So that is basically what a continuation is. And that is, like you saw, is behind the scenes, not something you can directly use. That's exactly the same idea in the case of Java as well. So what does Java do? Java takes a very different approach. And in this case, Java now has virtual threads. Ooh, what are virtual threads? Virtual threads are super lightweight threads. You said, whoa, wait a minute. Why is it super lightweight? Because the word lightweight was taken. So they had to think of something better than lightweight, so they said super lightweight. Maybe in the future we'll have a super duper super lightweight, right? But for now we have a super lightweight. So it's a super lightweight, so what does that mean? Well, in the past, when you allocated a thread, when the task blocks, the thread was blocking with it. And as a result, the thread was being underutilized. And when the thread is blocked, you're like, oops, that's not good. The program is not responding. It is not doing a lot of requests. Help. We said, no worries, let's create more threads. And those threads can block and wait on their task, but we create more threads. But there's only so many threads you can create. And as a result, you couldn't get really good performance. What do virtual threads do? Virtual threads, unlike real threads are at the operating system level. Virtual threads are at the JVM level. Now, before we dive into this, I want to take a slight detour. And the detour is to think about if in computer science, let's say we want to give an award, who deserves the award? And I will tell you, there's only one person who's worthy of it, in my opinion. Because, unfortunately, he passed away. His name is David Wheeler, a British computer scientist. Because what he said has an impact on us every single day. Every breath you take in and out as a programmer, you're living his statement. So what did he say so profound? Here's what David Wheeler said. David Wheeler said, in computer science, he said, we can solve almost any problem. That's only because he's modest. I think you can solve any problem. You can solve almost any problem by using one more level of indirection. That's what he said. This to me is absolute mind-blowing. To be able to figure this out, right? So he said, in computer science, you can solve almost any problem by using one more level of indirection. Let's think about it for a minute. Let's think about procedural programming. So in procedural programming, like C, what did we use for a level of indirection? We use pointers, isn't it? So I'm not suggesting we all enjoy using pointers, but nevertheless, pointers are powerful, isn't it? So what does a pointer do? You can take a pointer, and you can point to a function, and you can call the function through a pointer, and then you can take the pointer and point to something else. And you can use the same pointer to make the call, but it calls a different implementation than that one. That's a level of indirection. Your code doesn't have to point to something else in the code level, but the pointer can be modified to point to different things. You say, okay, that was cool. But if this guy's statement is so universal, we should see this in more places, isn't it? In object-oriented, right? So in object-oriented programming, what are we doing? So in object-oriented programming, we absolutely should be able to see indirection, isn't it? And we do. This is called polymorphism. Because what does polymorphism say? Polymorphism says, go ahead and call the method. But the method that's called is not based on the type of the reference at compile time, but based on the type of the reference at runtime. We call this dynamic binding. So dynamic binding gives us the level of indirection. My code is compiled, it's the same code, but depending on the object being passed in, it ends up calling different functions. That is the power of polymorphism, isn't it? And you say, okay, great. That means in functional programming, right, there's got to be a level of indirection too. Because after all, if this is such an interesting concept, shouldn't we be seeing this in functional programming too? And the answer is yes. And that's basically what lambdas are. Because I can pass a lambda to you. You can call the lambda right away, or you can postpone or not call it at all, or you can pass the lambda to some other function. But I can pass a different lambda to you the next time I call the function. Your function is still the same, but depending on the lambda I pass in, you may execute a different chain of actions. So that begs the question, in asynchronous programming, there's got to be a level of indirection. And the developers behind the Java language finally decided to apply a level of indirection to asynchronous programming. This is basically what virtual threads are. So why do I say virtual threads are a level of indirection? The reason is rather than running your task on a thread, run your task on a virtual thread which runs on a real thread. That's your level of indirection. So think of a virtual thread like a horse rider. I live in a neighborhood where people have horses. It's always like, wow, look at them. They're riding their horses, right? So this is a horse rider. So virtual thread is like a horse rider. So what happens? Your task is given to a virtual thread. When your task blocks, your virtual thread blocks and says, I'm going to wait for this task to finish. But the virtual thread is mounted on a career thread under the hood. When the task blocks, the virtual thread blocks, but it unmounts itself from the real thread and says, bye-bye, you can go do anything you want to. I don't need any service right now. What are you doing? I'm going to sleep here with this task. And when the task completes, the virtual thread says, I'm ready to run. I need some help. And a career thread is provided, and the virtual thread mounts on it and executes it. So there's mounting and unmounting happen continuously when it comes to virtual threads. Let's take a look. And just to get a feel for it, how does that really look? We'll take a look at that example. So I'm going to use a trivial example to illustrate this because it's the really nature of non-blocking. Whether you perform an I/O, whether you call into a database, whether you're writing to a file, whether you're going to log, it doesn't matter. But this is something that allows you to really do the mounting and unmounting. But let's entertain this thought just for a minute. So if I want to write this code, I'm going to write a public, let's say static, oops, you didn't see that, static. And let's say in this case, do work, which takes an index as a value. And within this, I'm going to just perform an I/O. Actually, you know what? Let's do an I/O just for the fun of it. So what am I going to do here? I'm going to say, first of all, output will print the index, first of all, plus, and we will say enter. And once I enter, I want to say in here a thread, let's say thread.current thread, right? So thread.current thread. So I'm going to really call and print out the thread of execution in this code right now. That's all I'm doing. Similarly, I'm going to say exit, right? I want to say, I'm done, I'm exiting. That's what I want to do. Maybe I'll call it as a Z exit, so it's the last one to be printed. But then I'm going to say try, and I'll say a catch, but I'm not interested in doing anything with the catch, so we'll simply ignore that for a minute. But within this, I'm going to say java.nio.file.star, and I'm going to say a files.lines.count. And I'm going to then say over here, let's say a paths.get, and let's simply say sample.java, which is the file itself that I'm interested in reading at this particular point. So that's my code. So we are reading the file, and then we are going to display it. But right after this, I'm going to say be after, right? And I want to print out what it is after I execute that code. So let's give it a try right here. So what am I going to do here? I'm going to say var, let's say max equal to 10. Let's just do a small value for now. Max equal to 10. And then I'm going to say, in this case, let's say a var executor, let's say service is equal to executors. So we'll go ahead and say executors. So for this, we'll say java.util.concurrent.star. We'll bring that in. So executors dot new fixed thread pool. And then what are we going to do here? I will say this is going to be a pool of max threads. So we got an executor service. Executor service, let's go ahead and say dot shutdown. And we'll say executor service dot await termination and termination. And we will provide a generous time unit dot seconds for it to finish up. So nothing really exciting in this code, as you can see, right? So we start this and we wait for it to finish. And of course, await termination tells us we need to, well, it cannot find the symbol. It says await. What did I miss? Oh, seconds. You restored SEONDS. You restored faith in pair programming for me. Thank you. And it's complaining, I need to handle an exception. But as experienced Java programmers, we know exactly how to take care of it. So that's my code right there so far. But what am I going to do? For, let's say I equal to 0, I less than max, I plus plus. And I'm going to simply say index equal to I, and then executor service dot submit. And what am I submitting in here? Do work, and I'll pass the index to it. That's our code, right? Nothing really exciting. So we are just making the calls and asking the response back. Let's take a look at what this is going to do for us, and let's take a look at what's going to happen when we use regular threads. So I'm going to just run this on the command line, if you will. I'm going to sort it, and I'm going to display the results of it that we're going to see right here. Actually, let's go ahead and change something. I was messing with version. So Java 22, let's say. Let me see if that works. Internet is unreachable. Well, duh. Okay, let me just connect that. So essentially, in this case, I'm going to see what version of Java I'm using right now in this example. Okay, so let's go. So here is our execution. I want to run. Let's take a look at what it tells us. Let's just quickly sample this, if you don't mind. Notice, actually, let's make this a little bit more civil. So I'm going to say index, and I'm going to just put a little space here so I don't have to look at it and stare at it. Where am I? Let's go to, there we go. So let's put a little space here and here as well. Got it? Okay, so let's go ahead and run the code and see what the output says. So when you look at it, let's just take a little bit of a sample here, if you don't mind. Let's look at 3. I'm just randomly picking one. What do you notice in 3? It was executed by thread 4. So what did thread 4 do? Hi, come on in. And it stays with it until the end. Also known as very inefficient, right? Let's take one more. Let's look at 5. That's executed by thread 6 entirely. What about 8? That's executed entirely by 9. So you get the point, right? That's pretty darn inefficient. So what does a thread do? It simply says, I'm going to stick with you until the end. Now we say, no, we don't want to do that. Notice, I am not going to touch this code. I'm not touching that code at all. But I'm going to go down here, and I'm going to make one change. But before I make the change, I want to talk a little bit about this. I'm going to give you a very gross example. If you don't like gross examples, I recommend you close your ears tight or leave the room for 5 minutes and come back. Because once you hear it, you will never be able to unhear it. You're being warned. Don't go tell the conference organizer, never invite this guy again. His examples are gross. I like giving gross examples because people never forget them. I mean, people come to me after 20 years. I remember this gross example you gave me. It's like, yes. You're still here, so I warned you. Virtual threads are like Q-tips. You take a Q-tip. Maybe you have a nice friend. They take a Q-tip. They clean their ears. And then they ask you, should I save this? Should I reuse it? Like, oh, no, that's gross. It's use once and throw it away. And they say, but why shouldn't I reuse a Q-tip? Like, dear friend, no. Q-tips are cheap. Throw them away. And it's unhygienic to reuse it. You will spend more money sterilizing a Q-tip to reuse it. Virtual threads are like Q-tips. Use them, throw them away. If you have a friend who says, I want to reuse virtual threads. The chances are, let's not go there. So the point really is, virtual threads are created and disposed of. So as a result, if you notice, if you said executors dot, notice you have the new fixed thread pool, all right? But you have a new virtual thread per task executor. What does that say? Ding! Here's the new one for you. Here you go. Here you go. Here you go. You keep asking, you keep getting a new one. It's a use and throw. But it's under the umbrella of the executor service. So what that means is, you have an existing code that is using executor service. You don't have to do a whole lot, except change that line of code to say, don't use a pool, please. Use a virtual thread per task executor. So every time you do submit, you get a new executor virtual thread. Isn't that cool? So let's go take a look at it. All I'm doing is making one change. That's it. In that sense, the thread is like an aspect in aspect-oriented programming. That's what it really is. You are not changing the code that's running up there. Instead, you are sitting here and flipping a switch. Synchronous, asynchronous, synchronous, asynchronous, right? So you don't have to put a lot of effort into changing it. So let's go back here and run the code this time. Let's take a look at the output and see what we notice. Let's take a random one again. Let's take 3. When you look at 3, what do you notice? Look at the virtual thread number, 32. So the virtual thread is attached to your task. And the virtual thread says, I'm here with you all the way through. But what did your code do? Your code says, I entered this function, I'm going to make an I/O call. And the virtual thread says, woo, I/O is going to take some time. And I don't want you to waste your resource. So notice what happened. You were using worker 4, and it unmounted from worker 4. And the virtual thread is waiting with you, while the thread 4 said, bye, I'm going to go help somebody else. And it went away. When the request was over, it got mounted on 5. You just leave the try block. And remember, when you leave a try block, there are stuff it needs to do. What if there was an exception? So it unmounted again and mounted on 6. By the way, don't look at this example and assume the mounting is sequential, right? The next one would be 7. No. It could be any thread. Let's pull one more example and take a look at it. Let's look at 5 again. Look at 5. You have 34, which is your thread. Let me pull this up to the top. You have 34, which is a virtual thread, but you are in 6. Then jump to 4, then jump to 5. And you can see how it was mounting and unmounting. So as a result, it's mounting and unmounting and mounting and unmounting. And benefit of this is your threads are useful to go serve other requests. As an example, just like today, except that I came here in the afternoon, but since I travel cross-Atlantic often, a few months ago, it was 2 a.m. I had been traveling for a good 36 hours. And at 2 a.m., I want to go sleep. That's what I want to do. Because I got a talk to give at 9. I better sleep and go. So I pulled into this hotel. And there was one clerk, and there was a customer in front. And I'm the guy who travels with my passport on my pocket when I travel. So I'm like, I'm ready. Check me in. I want to go sleep. And I'm standing there. And the clerk says, excuse me, dear customer, I need an ID from you. And the customer said, what do you need again? I need an ID. Oh, you need an ID. Like a passport. Oh, a passport. And the person literally starts a binary search of where a passport is on their body. Passport. I don't have it here. passport, and the person is watching the binary search. I'm like, kill me now. I want to go to the room and sleep. That's the way thread in Java was. If this person had been in this session, they would have not done that because they know how to be a virtual thread and not that sucky thread. That person could have said, excuse me, customer, while you do binary search, please continue, and could have switched over to the next terminal, may I help you, and could have checked me in, right? But instead was stuck on that customer. But look at these threads, they're nice. They keep going because they don't get stuck on that and other threads can execute. So then, what did we achieve with this is the question. Let's think about it. So asynchronous programming, right? So asynchronous programming, what do we gain from this? Asynchronous programming has an impact on scalability and availability. How so? It has an impact on scalability because you need fewer threads to get your work done. You can do more requests on a box. Your application is more scalable. If you're developing Spring application, just turn on one flag, use virtual thread, boom. It can start now addressing more requests. Same thing with other things like Quarkus and Micronaut and so on. But what about availability? If a lot of threads are blocked and a lot of requests are blocked and waiting, they're going to error out. So you got an issue of availability as well. This helps you with availability and scalability. But until now, programming asynchronously was very difficult, right? Let's think about it. In Java, you have the file asynchronous access that you can use for async I/O. When you do, what do you use? You call a function and pass a callback. When you call a function and pass a callback, what happens? Callbacks are hard to program with. They get worse when you have to make more asynchronous calls, right? So you want to make more asynchronous calls. What happens in the callback? They get even more worse when you deal with exceptions. We call them fondly, right? Fondly as callback hell. This is not the place where you want to live. Callback hell makes you dread your code. But then Java has another solution, which is completable future. Let me ask you a question. Please raise your hand if you have used completable future and were happy when you finished using it. See? 2 people. You need better life. Why are we not happy using completable future? Completable future is great as long as you don't use it. The minute you start using it, it's like, ooh, it's functional style. Ah, awesome. And you start looking at the code, and there is the code happy path, and there's the unhappy path, and the code becomes like this, right? And you're trying to reason about the code, and you're looking through it, you're scratching your head, and you're like, what's going on here? I am not even kidding with you. I was giving a talk yesterday in Chicago, actually. And a guy came to me and said, at the end of my talk, he said, oh my gosh, I wish I had known this before. I said, why? He said, I wrote the code for asynchronous programming in my work, and when I finished, I quit because I know I cannot maintain this anymore. At least he was honest about it, right? So it causes people to job switch. But the guy was very wise. I wrote the code, not a place to work anymore, right? I don't know what this pattern is called. leave the building burning pattern, right? You're like smoking, throwing up, like, boom, right? And then you walk away. I did that, right? And that's what this dude did. He's like, I wrote this code, and I know this is not maintainable, so I walked away. I'm happy in my company right now. And I said, what do you do? And he said, I'm writing my next asynchronous code, right? So like, no. So that's horrible, right? So I hate to say this. Completable future has no future. Seriously. Because that's complicated code. And I want to talk about one more thing before we do. So if you really think about it, back in time, the structure, this is the last thing I'll make before we finish. The structure of parallel, imperative style code was very different from the structure of sequential imperative style code. We saw that too, right? That's extremely different. And in Java 8, the structure of parallel functional style code is the same as the structure of sequential functional style code. This is thanks to the Java streams, right? So streams gave us the ability to write the code sequential, and boom, parallel stream within constraints. You're able to see the code execute in parallel. Guess what? Functional style code is awesome as long as you don't have to deal with exceptions. The minute you bring exceptions, the code becomes dysfunctional. It's not functional anymore. And the people who cling on to it are hopelessly clinging on to it, right? But it turns out I/O is full of exceptions. Every time you do I/O, you got to deal with exceptions. Imperative style, you could say, as complex as it is great for dealing with exceptions, because that's the right tool, that's the right choice, isn't it? So here's the beauty. Thanks to virtual threads, the structure of imperative style asynchronous code, that's a beauty, right? It's the structure of asynchronous code is the same as the structure of imperative style synchronous code. And why is this a cool thing? And how is this possible? I would say that's because of virtual threads. So essentially, Java has leveled the playing field. If you noticed, I did not change the code that was making the I/O. I didn't touch it. I was elsewhere, and we flipped synchronous, asynchronous. So you're able to flip that switch and be able to achieve synchronous with asynchronous without having to change the structure of the code. What that means is, as an architect, you can defer your decision. When your decision is cheap to implement, it's easy to postpone it. If the decision is expensive to implement, you're going to be eager to make the decision early. But in architecture, we know last responsible moment gives us advantage. So Java really is helping us architecturally to say, program synchronously, and if that's adequate, leave it that way. But if you want to be asynchronous, we can make that happen without much effort. And you don't have to change a lot of code to do it, because just an aspect you can flip and you can achieve that. And to me, that is remarkable from the architecture point of view. And that's basically what virtual threads provide. They make really good sense to use for I/O operations. Don't use virtual threads for computation-intensive jobs, because they are going to be using your CPU constantly. It makes no sense to use them for computation intensive. But if you're performing any kind of I/O, it makes a lot of sense to use virtual threads when you need to run the code asynchronously. So the benefit is your code looks like it's synchronous, but it's got all the benefits and advantage of asynchronous. And making that switch is literally inexpensive in Java because you don't have to make any changes to the code that's making the call. You just have to change the threading model. And that's a power you have. Hope that was useful. Thank you.